Thank you, everyone. In this presentation, what we're going to do is that we're going to dive a little bit deeper into the implications of electrification for supply and infrastructure. And as we've seen in the previous presentation, the way that we can reach the targets, which we have seen are feasible, is by electrification and particularly providing that additional electricity with renewables. This is going to be mainly due with solar and wind power, which are going to be the main ones that are going to help us reach these targets. We could also see in our analysis that while, as I said, solar PV and wind were key, so any limitation that we put on the maximum capacity that we can install is going to have an impact on the cost and the feasibility of the transition. Limitations in other technologies such as nuclear, biomass, or even CCS, they wouldn't significantly affect the trajectories. So the main takeaway message is that wind, both onshore and offshore, and solar PV are going to be the main technologies that we need to provide this additional electricity, and other technologies are going to have much a secondary role. The fact that we would increase our penetration of intermittent renewables is going to lead to a much increased flexibility need. And these flexibility needs are going to be very different depending on the particular mix of solar and wind that we deploy. In the plots in here, we can see two examples of very different power systems. On the top, it refers to Germany. The bottom one represents Spain. And in our analysis, we did something very interesting, which is to get how much were the flexibility needs for different time horizons. So the first bar in the plot corresponds to the fluctuations per day that need to be covered. And then we have weeks, months, and finally the flexibility that is needed to cover the year. And as we can see, the flexibility needs for Germany are much larger than for Spain. This is also due to the larger demand, of course, but they are much flatter. They go down, but in the case of Spain, we can see that there is a much higher need to cover for these hourly fluctuations. This is due to the fluctuation of solar PV, which has a much larger share in Spain. So the idea is that we will cover for these flexibility needs using a mix of different technologies. So we can see here that we have some technologies that can be used throughout all the different horizons in kind of the same way. So for instance, in Germany, we can see that hydrogen is used throughout all the horizons a lot, while other technologies are much more useful in the shorter term compared to the long term. And the main example here is batteries. So as we can see, the piece in yellow, this is the most efficient way of covering the hourly flexibility needs. But this will not be enough. So there will be other needs. In Spain, it's also very apparent to see how cross-border exchanges, cross-border interconnections, obviously they can balance the different profiles of renewables throughout the years and across Europe, and they can be very useful across all the scenarios. Also, it's very interesting to see that the hydro reservoirs are very useful in Spain. They are used in the short term, but they are also even more useful in the long term, where they cover a very wide proportion of the total flexibility needs. So the main takeaway here is that we would have an increased flexibility need, which will materialize differently in the different horizons considered, and that technologies for flexibility need to be installed in a coordinated mix, which needs to include the different technologies in order to serve these different technology needs. We're going to have batteries and also EVs. We will talk about EVs in a second, which are very useful in the long term. Also, demand response is really key for this very short term. We can see that in pink. Cross-border exchanges are useful across all horizons, as is hydrogen. So policies should encourage this investment, and this investment should reflect what is happening in generation, because more solar PV means more short-term flexibility. Also, there is a trade-off between these flexibility options, and another of the analysis that we performed is to see how much does EV flexibility bring to the table when studying how to cover the short-term flexibility needs of the system. And what we considered were different hypotheses with respect to how EVs would be charged. So in particular, we tried 3 different scenarios. One where the EV fleet would behave with medium flexibility, and then we would have more inflexible behavior and more flexible behavior to compare. So what we could find was a confirmation of what intuition would bring, which is that a higher flexibility in the charging and vehicle to grid in the EVs can very clearly reduce the need for batteries. So batteries will always be needed, so they will not substitute completely, but they can bring down these needs for investments. And actually a higher EV flexibility could cut down system operation costs by 2.5 billion a year across Europe. So this issue about EV flexibility is going to become very important, and policy should make sure that flexibility in EV charging is incentivized.
Also, we need to, when we consider the impact of EVs, we need to consider what happens at the lowest granularity. And one of the things that we did was to study what is the impact on the distribution grid of these technologies. And the main takeaway here is that we should really avoid situations where there is a synchronization of loads that would be controllable in principle. So the type of strategy that is followed with charging or not charging EVs will have a very large impact in terms of the needs with respect to the distribution grid, and also with respect to how much storage capabilities EVs can provide that we would need to provide with other technologies otherwise. Also, as I was mentioning before, the grid is a very efficient way, the transmission grid is a very efficient way of providing flexibility throughout time horizons, since the hourly horizon to the yearly one. And we could find that we will have needs for grid investments of around 200 gigawatts of cross-border transmission, independently of this scenario. So this result is very robust. So we will need cooperation and support to be able to install these reinforcements so that this cross-border trade can support the flexibility needs that investing in renewables will bring. And by the way, these 200 gigawatts of new capacity is in line with what has been planned for 2050. So we are just confirming that this will be needed independently of the scenario. This is very robust. And then last, we have examined in detail the role of hydrogen and hydrogen infrastructure. And we found that before we looked into this, there was like a very clustered opinion about the future role of hydrogen, with some studies presenting hydrogen as the solution for the transition, with some others practically ignoring it. So what we could find is that robustly, our models say that the true role of hydrogen will be in the middle. As you can see here, for these different scenarios, the share of hydrogen will be relatively low. So in the scenario with the highest carbon price, the C400 lean, the price of hydrogen, the share of final energy consumption that will be covered by hydrogen will be less than 12% in any of the cases covered. However, even if the share is low, we see that the role that it will play for decarbonization will be key because of the ability to apply it in some really hard to abate applications, such as high heat industry or some means of transportation like shipping and so on. So it's limited in its role, but it's critical. And then when we see what is the optimal strategy to provide for this hydrogen, when we consider different scenarios, we can see that the most efficient, the most cost-efficient way would be to produce that hydrogen domestically using renewables. We could actually see that if we increase the share of hydrogen, the most efficient way would be to first build electrolyzers close to renewables, and then as we continue increasing the share of hydrogen, we would move hydrogen to the demand centers. Also, with more hydrogen production, there is less of a need for network investment in this carrier as well. And even if it's less efficient, some trade within the MENA region would be not so far away from being costly optimal. And as you can see there, things change a bit depending on the scenario. So, for instance, this would be the high PV scenario, where this would lead to particularly less inputs from outside of the EU. And also in here, it can be seen quite well that hydrogen works providing flexibility at very different horizons. This high PV scenario shows how we can also use it for the yearly storage as well. So, as main takeaways, the most important one is what we have been seeing time and again during the rest of the presentations by my colleagues. Renewable power generation and electrification, they go hand in hand, and they are going to be the way in which we're going to be able to reach our decarbonization targets. But this is going to lead to very intense needs for flexibility in different horizons. And this nature of flexibility is going to lead us to be able to build a different portfolio of technologies that will complement each other. Grid investments are going to be needed independently of the scenario, and we could verify that the targets that we have for 2050 really make sense with respect to the evolution that we can see in the production of energy. And we are going to be very careful. We're going to be needing to be very careful with the policies that we put in place for electric vehicles, because the flexibility that they can provide is going to be important both at the macro scale and also at the micro scale of the grid, with a very important impact coming from prosumers and their strategies. And finally, the role of hydrogen is going to be limited in terms of share of final energy consumption, but very important in terms of abating hard-to-abate sectors. And the most cost-effective strategy is the domestic production, first with electrolyzers in renewable sites, and then scaling up to demand centers. Thank you.